Hello everyone. Let us now proceed to the last part of this lecture, our introduction to entropy. In order to start our discussion, let us recall our Carnot engine, and the thermal efficiency of a Carnot engine is equal to 1 minus Tc over Th. So for a Carnot engine, the thermal efficiency is only dependent on the working temperatures of the upper and lower heat reservoirs. Okay. Based on this, based on the definition of a thermal efficiency of a heat engine, 1 minus Qc over Qh. Okay. For a Carnot cycle, Qc over Qh is also equal to Tc over Th, or absolute value of Qh over Th is also equal to absolute value of Qc over Tc. Now, if we just base it on the working fluid, okay, we know that Qc should actually be negative kasi palabas siya ng system. Okay, so without the absolute values, you will have QH over TH is equal to negative QC over TC. And rearranging, you will now get QH over TH plus QC over TC is equal to 0. Take note now na QC here should be negative. Okay, now for a Carnot cycle, recall if you draw the PV diagram of a Carnot cycle, you have working between these two temperatures, you have TC and you have TH. Okay, so you will have this process. Okay, 1, 2, 3, 4. So meron tayong cyclic process ngayon for the Carnot engine and the Carnot cycle. So for example, if this is the initial point, okay, babalik din siya eventually to the initial point. Therefore, all the state functions will return to their original state once a complete cycle has been achieved. Okay. So for a complete cycle of any reversible heat engine, the working fluid of the cyclic engine will periodically return to the original state, and the respective properties will then return to their original values. Therefore, the sum of all the changes throughout the cycle is now equal to 0. However, we have also derived earlier that QH over TH plus QC over TC is equal to 0, and the sum of all the differential changes in Q and C per step in the cycle must also now be equal to 0. Kung ngayon, if all properties will return to their original state, there must now be a property that is directly related to the quantity Q over T. So again, so for any hypothetical heat engine na reversible, all properties will return to their original state once the cycle has been completed. So since with this, dq over th plus dqc over tc is equal to 0, okay, or the cyclic integral of dq reversible over temperature is now equal to 0. So ngayon, ano tong quantity na dq rev over t na we can define something as a new state property. And this is now what we call the definition of entropy. And dST, or the total entropy, is simply equal to the reversible heat change, dq rev, over temperature, and rearranging, TdS total is equal to dq rev. Okay, so now, how do we evaluate delta S or ds? For any quantity whose cyclic integral is 0, as shown by our previous derivation and dq over t, that quantity's change is dependent only on the initial and final state and not the path taken by your process. Okay. So ngayon, dqt, cyclic integral nun is equal to 0. Therefore, the integral of ds should now only be dependent on the initial and the final states. Meaning, delta st, okay, the total delta S is now equal to just the final entropy minus the initial entropy. And that is equal to the cyclic integral of dq rev over temperature. So meaning, okay, delta S is a state function. Okay, so now, based on the definition of entropy, dSt is equal to dq rev over t. And for reversible processes, delta St is equal to the cyclic integral of dq rev over temperature. Now, what if irreversible yung path na iti-take ng isang process? So, when a system undergoes an irreversible process between two equilibrium states, the entropy change of the system is evaluated by application of the equation above to an arbitrary chosen reversible process that accomplishes the same state change as the proposed process. So you won't evaluate the integral for this path, okay? You will choose an arbitrary process that will accomplish the same change in state. And that is how you will now evaluate the delta S for an irreversible process. Now, for heat reservoir, okay, the entropy change for a heat reservoir is always given by Q over T, whether the process is reversible or irreversible. Now, what if the process is adiabatic and reversible? So, pag adiabatic yung process, dq rev is equal to 0. Pero, kung wala tayong heat loss, wala tayong heat transfer, the quantity Q over T or dq over T will also be equal to 0. Thus, ds is equal to 0. So this is why adiabatic reversible processes are also equivalent to isentropic processes. They are one and the other. Sige. Now, how do we evaluate entropy changes for ideal gases? So consider the first law of thermodynamics again. So for a reversible process, du is equal to dq rev minus pdv. Again, pdv ito yung dw. So du is dq rev minus pdv. Now, let's make some substitutions. For the definition of enthalpy, H is equal to U plus PV. Taking the derivative of both sides, you will get dH is equal to du plus chain rule ng dPV, so PdV plus VdP. And then substituting, okay, this, you will get dH minus PdV minus VdP is equal to dQ rev minus PdV. Okay, so lipat lang dito sa kabila, tapos substitute dito in terms of du. Then you will see that ito, pwede natin i-cancel out, see negative PdV. And rearranging for dq rev is equal to dH minus VdP. Okay, now how do we simplify this? Recall that dH can be expressed in terms of CpIg dt for an ideal gas. Okay, now we have an expression for temperature, volume, and pressure. Let us use the ideal gas law para ma-reduce lang into two variables. So from ideal gas law, V is equal to RT over P. And again, enthalpy is dH is equal to CpIg dt. So substitute itong RT over P dito. You will get dq rev is equal to CpIg dt minus RT over P dP. Okay, so now, paano to? Let's rearrange. Divide everything by the temperature. Okay, dq rev over T is equal to CpIg dt over T minus R dP over P. And you can now evaluate the integral of both sides. Okay, integral of dq rev over T is simply equal to delta S. Integral of CpIg dt over T, okay, depende siya kapag Cp is constant or Cp is not constant. Then integral of negative R dP over P is equal to negative R ln P over P naught. So delta S is now equal to integral of T naught to T CpIg dt over T minus R ln P over P naught. Okay, and as you can see from here, how do you increase the entropy? So entropy increases from increasing entropy if you increase the temperature or if you decrease the pressure. Okay, and rearranging this, you can get delta S over R is equal to integral of CpIg over R dt over T. And ito, we have tabulated values of CpIg over R. Recall from our heat effects discussion. Okay, minus ln P over P naught. Okay, so for ideal gases, recall that if a Cp is a function of temperature, you have CpIg over R to be this polynomial function. And you can now have the integrated entropy change as such. So, integrate lang natin, you will get this particular expression. In some cases, in our textbook reference, Smith, Vanas, and Abbott, yung ginagawa niya, ina-express niya itong term na to in terms of a dimensionless temperature. So, tau is equal to T over T naught. And it's more useful, supposedly, for fixed point iteration. Especially kapag unknown temperature yung ginagamit natin. Okay? So now combining, again, delta S over R is equal to integral of CPIG over R dt over T from T naught to T minus ln P over P naught. So if CPIG over R is a function of temperature, you can have the integrated expression for the entropy change for an ideal gas, as shown. However, we can also simplify this. If it's constant Cp, you can remove this out of the integral to get the following. So delta S over R is equal to CPIG over R. We'll now be left with the integral of 1 over T. So ln P over T naught minus ln P over P naught. Okay, so now that we know how to calculate entropy changes for reversible processes, okay, or even entropy change for ideal gases, ano ngayon yung significance nito on the second law of thermodynamics? Okay, so let's try to now formulate a mathematical statement of the second law from thermodynamics. In order for us to do that, consider this scenario. Meron tayong hot reservoir, we have a cold reservoir, and naturally, heat will flow from the hot reservoir to the cold reservoir. Okay? So, by energy balance, equal dapat yung Q na lalabas sa hot reservoir as sa Q na papasok dito sa cold reservoir. So to evaluate, let's get the delta S of the overall process. And this is equal to delta S ng hot plus delta S ng cold reservoir. Ano nga yung delta S ng hot reservoir? Okay, that is equal to Q over TH, but Q ay palabas ng reservoir, so negative by the sign convention. Plus, delta S ng cold reservoir is Q over TC. Okay, the question now is delta S positive or negative or equal to 0? Okay. In reality, we know that this process is irreversible kasi hindi naman babalik yung heat from the cold reservoir to the hot reservoir. Okay? So with this, tingnan natin which one is hotter. Diba, yung hot reservoir. So TH is greater than TC. Meaning, if TH is greater than TC, same magnitude yung Q dito, magbaliktad lang yung sign. Okay? You will get the absolute value of Q over TH should be less than the absolute value of Q over TC. Okay? Meaning, delta S for this process should now be greater than 0. Okay? Now, what if baliktad yung nangyari? Supposedly, ginawa lang natin na from cold to hot. That's called that Q prime. Okay? So, for delta S ng process na yan is equal to negative Q over TC plus Q over TH. In this case, this relation will still hold true. Absolute value of Q over TH will still be less than absolute value of Q over TC. Okay? Pag ganito, mas negative ngayon itong value nito. Therefore, delta S will be less than 0. So delta S is negative. In reality, this process should not occur spontaneously. Okay? Wala tayong way for energy to transfer from the cold reservoir to the hot reservoir as is. Para ma-counteract, para kung gusto mong gawin yon, you need to have work added somewhere using your refrigerator or a heat pump. Pero since wala yan, okay, this process is not spontaneous. Now, using this, we can now develop the mathematical statement of the second law of thermodynamics, which is, for any irreversible process, delta S total should be greater than 0. Now, para tayo magkakaroon ng reversible process, so delta S for a reversible process should be equal to 0. And paano mangyayari yon for this heat reservoirs? Dapat, TH should approach TC. So kunwari, if you have 25-degree heat reservoir and a 25-degree heat reservoir, heat will flow in equilibrium or at least reversibly from one to the other. So you don't know kung saan talaga papunta yung energy kasi they're at the same temperature. Okay, so the greater the temperature difference between two heat reservoirs, the greater the entropy change. Okay? So every process should proceed in such a direction that the total entropy change associated with it is positive, and the limiting value of zero being only attained by a true reversible process. So, however, there is no process that is possible in which the total entropy decreases. Okay? So for all processes, delta S total should be greater than or equal to zero. And for reversible processes, this should be equal to zero. And for irreversible processes, definitely, the total entropy change should be greater than zero. Okay, so to evaluate the total entropy change, it is not only the entropy change of our system, but also the entropy change of our system and our surroundings. With that, since alam natin na for irreversible processes, the entropy should increase, okay? Unlike energy, which is always conserved, if all processes were reversible, the total entropy of our universe should always be constant. However, all of our processes are irreversible. Therefore, entropy is never conserved. Therefore, another statement of the second law of thermodynamics is the entropy or disorder of the universe is always increasing. Okay, let us now consider this scenario. We have the isothermal compression of air inside a piston cylinder device. If the work done by the piston is 1500 joules per mole of air, calculate A, the entropy change of air, and B, the total entropy change if the surrounding medium was at 20 degrees Celsius. So to start off with, let's calculate first the entropy change of air. So for the entropy change of air, let's assume to be an ideal gas, delta S air over R is equal to integral of Cpig over R dt over T from T naught to T minus ln P over P naught. However, we have an isothermal process, therefore dt is equal to 0. Thus, the entropy change of air, delta S air, is equal to negative R ln P over P naught. And we know that the delta S of our surroundings is equal to Q over T surroundings. Okay? So, before we calculate kung ano yung delta S ng air and delta S ng surroundings, we need to proceed first to our energy balance. So, from our energy balances, delta U is equal to 0 since this is an isothermal process, it is equal to Q plus W. Ang work natin ngayon is 1500 joules per mole of air, okay, which is positive. And recall that work for an isothermal process is equal to RT ln P over P naught. So W is equal to RT ln P over P naught, which is equal to 1500 joules per mole. And if we take a look at this, we can now obtain a value for R ln P over P naught, which is equal to 5.031 joules per mole Kelvin. Now, delta S of air is negative R ln P over P naught, thus the delta S of air is negative 5.0310 joules per mole. So ngayon, tingnan natin, negative yung value na calculate natin for the entropy change of air. Does this mean na hindi na feasible yung process kasi negative yung delta S? Okay. So for us to determine that, you have to calculate kung ano yung total entropy change ng universe for this scenario. And in this scenario, there are two entropy changes. One is the entropy change of air, and the other is the entropy change of our surroundings. So we now need to get kung ano yung entropy change ng surroundings. So the entropy change of the surroundings is equal to Q over T surroundings, but not just Q, it should be Q of the surroundings. Okay. And the change in heat of the surroundings is equal to negative Q of the system. Okay. Now, negative Q of the system, Q system is equal to negative Q, okay, it's equal to negative work. Okay. So negative ng work is 1500 Ito yung Q na system, negative. So, Q na surroundings natin is 1500 joules per mole. Okay? So meaning, throughout the compression process, heat was being released to our surroundings. And this makes sense. Because if you operated this piston cylinder adiabatically, the temperature should increase. Okay? However, since they maintain yung temperature at 25 degrees Celsius, so therefore, heat is constantly being released throughout the compression process. And that total heat is 1500 joules per mole. You can now calculate kung ano yung delta S sa surroundings, which is Q over T surroundings, which is equal to 5.1168 joules per mole Kelvin. And combining delta S total is equal to delta S surroundings plus delta S of air. You can now get delta S total, which is 0.0858 joules per mole Kelvin, which is now a positive value, meaning the process is actually feasible. So, pwede itong process na to. Now, what would happen if the surrounding temperature, okay, was different? Or, should the surrounding temperature be, let's reword that, if the process to be completely reversible? So ngayon, irreversible yung process. So what does the surrounding temperature need to be para maging purely reversible yung process natin? Okay, so ngayon, babaguhin lang natin yung surrounding temperature. So, you will now change this value. The Q of the surroundings will still be the same na 1500. So, magagawin lang natin 1500 over T ng surroundings, okay, minus 5.0310 should be equal to 0. And with this, you will calculate T surroundings is approximately equal to 25 degrees Celsius. Ano ang significance ito? Equal ngayon yung temperature ng air sa loob ng piston cylinder natin sa surroundings temperature. And for heat transfer to be reversible, kailangan equal yung dalawang values nila. Okay, so for a completely reversible process, dapat equal yung temperatures ng nasa loob ng system at nasa loob ng surroundings. So the heat transfer is so the total process is reversible. Okay, now consider what would happen if the surrounding temperature is 30 degrees Celsius. Okay, so this will not hold true anymore. So delta S total natin ngayon is equal to 1500 over 30 plus 273.15 minus 5.0310, same pa rin delta S ng air. And you should get negative 0.083 joules per mole K. Meaning, delta S is less than 0. Ibig sabihin, hindi pwede yung process na to. Bakit? Okay. Physical manifestation nito, if the surrounding temperature is at 30 degrees Celsius and the temperature inside the system is 25 degrees Celsius, di ba dapat ang heat transfer natin from 30 to 25 degrees Celsius? Pero yung process natin sa loob, okay, for you to maintain a compression process isothermally, you need to be rejecting heat to the surroundings. Pero nangyari dito, for you to maintain the piston cylinder air at 25 degrees Celsius, you have to reject the energy to the surroundings. But you cannot physically reject that to surroundings that is higher than the temperature that you want it to maintain. Okay, so hindi pwede mag-flow yung heat from 25 to 30. Ito yung gusto mo mangyari pag ganito yung process, kaya nagiging negative yung total delta S natin. Okay, let's now have the last example. We have the adiabatic reversible expansion of methane to 1 bar from 550 Kelvin and 5 bar. Assuming that methane is an ideal gas with a temperature-dependent heat capacity at these conditions, determine its final temperature. Okay, given na sa atin yung ideal gas heat capacity constants. Now, we have a reversible adiabatic process. And for a reversible adiabatic process, this is also an isentropic process. Okay. So since the process is reversible and adiabatic, It's an isentropic, thus delta S of the process is equal to 0. Okay. Adiabatic siya, so wala tayong entropy change ng surroundings. So entropy change ngayon ng system is also equal to 0. So we have an unknown final temperature. Okay. So let us use the integrated form, the entropy change for ideal gases. So recall our previously derived equation as such. Okay, so unknown temperature. So delta S over R is equal to 0. P is 1 bar. P naught is 5 bar. T naught is 550 Kelvin. Okay. So we'll now rearrange this such that this temperature is now isolated. Okay, and then rearranging, you will get this following expression. And using an arbitrary guess of 400 Kelvin, okay, do fixed point iteration until convergence up to 0.1 Kelvin na absolute difference lang. Okay, so again, recall the steps in fixed point iteration. Yung 400, plug in muna dito sa right hand side. You'll get a new value of T. And then, you will compare the two values. If hindi pa sila pasok sa tolerance, plug ulit dito sa right-hand side until you have your convergence. Okay, using 400 Kelvin as your initial guess, you will now get a summary of iterations as shown below. Okay, so the final temperature is now 411.31 Kelvin. You can also do this in another way. You can use a dimensionless temperature, okay, using tau, and using an initial guess of tau of 1, using a relative tolerance of 0.001, okay, you will get the final value of the temperature to be 411.21 Kelvin. So both methods are valid, and mag-iba na talaga yung sagot depende sa magiging set criteria mo for convergence. Okay, and that ends our lecture on the second law of thermodynamics. Okay, for this part, our next lecture again will be still the second law of thermodynamics, but now for open systems. Okay, on the energy analysis for open systems. So if you have any questions regarding this lecture for the past three parts, please contact me as soon as possible. Thank you.